Okay, this is a follow-up video lesson for the rational exponents section of the textbook. Part two, here we're looking at just a review of the two rational exponent laws. I'm going to go through this investigate, which you may at this point have had a chance to do in class. I'm going to give as many different ways that I can express that formula for you to compare to what you've come up with. I'm going to go through example 3, solving a financial problem, which is found in your textbook, and make sure that you know how to answer a related question with the compound interest formula. And then I'm going to answer number 12, which is found in your textbook on page 377. So let's go back and review here. Okay, without going into the why, the how is when we have a rational exponent of 1 over n. That requires us to use the nth root of our base. There are conditions there. At least we need to know that for our purposes we'll use a as positive values, and n will be a natural number, okay, which is defined over here. So our exponent will never involve a decimal and a fraction at the same time. Natural numbers are whole values starting from 1 and counting up. The second rational exponent law, that's really just a special case of the first, is that if we have our power separated out in that form, or possibly this form, both of those are equivalent, okay? 1 over n multiplied by m, and m times 1 over n. Both of those produce m over n, which is our original exponent. So this would require us to take the nth root of our base, raise it to the exponent m. This would obviously require us to first evaluate the inside power and then evaluate the nth root. So they look very similar. Both are going to involve the same operations, just the order will change. So those are our two definitions that you need to know. We've gone over examples from 1 and 2 in the textbook. Now in example 3, we need to know what the compound interest formula is. So the amount of an investment is what is going to be also called future value. Okay, we'll do a little bit of financial math in this course. So future value is what the investment grows to over time, starting with a principal amount P, okay, which is current value. And then we have a base, which is 1 plus the interest rate, where our interest rate is a decimal. Okay. And then we have an exponent n, where n is number of compounding what are called terms or periods. Okay. Okay, so in this case, under annual compounding, it would compound once every year. And compounding interest has money growing exponentially, according to this formula. When we first put in our amount, we have to know that, okay, growing to is in the future. Growing from is the current value of 700. The annual interest rate is not known, so leave it as 1 plus I, and in 5 years. So assuming annual compounding, there would be 5 annual periods, so there'd be values of n equals 5, a equals $900, and p equals 700. So that's how I'd start my problem, is just to list what I know. In this case, the unknown is the base. Okay, so take note that collectively we have our power, which is the whole thing. Okay, the power is the base combined with some exponent. So if we want to think about an arrow diagram here, if we started with our interest rate, the first thing we're doing to it is we're adding 1. The next thing we're doing is we are taking that and evaluating the fifth power. Then we're multiplying by 700, and that is producing our value of P. So the first thing we would want to do in reverse is to divide by 700, and then we're going to do the opposite of raising something to the fifth power, which would be raising it to the 1/5, also called the fifth root. And then finally, to get back the interest rate, we would subtract 1. So that's sort of the plan to get our interest rate. So again, first step, I'm going to take 900 divided by 700. That's going to produce 1 plus I to the fifth. After that, I'm going to take that fraction and I'm going to apply a 1/5 exponent to both sides. Also, a fifth root would be another way of seeing that. And then we're going to take that result and I'm going to subtract 1. Now I like the strategy of do all your simplification and rearranging first and then evaluate the numbers. Okay, there I've worked at the rest of the problem. So I'm putting the exponent in brackets just to remind you that when you enter that on the calculator, you are going to want to put that in brackets unless you use the decimal equivalent. So you could use 0.2. Okay, so you use 0.2, or you could use the fifth root of the value, or you could put bracket 1/5. So there's different ways of using that on your calculator, and quite clearly we have to use a calculator here. Carry lots of decimal places because this is financial application, and when you start to round, you find that interest rates don't actually produce what they're supposed to over a 5-year period. So use lots of decimal places, maybe even more than 3, and then round in your final answer. So I get 1.286 approximately being equal to 900 over 700. Then I evaluated the fifth root of that, get about 1.052. Take away 1 from that, and we're getting the decimal form of the interest rate, which as a percentage we multiply by 100 just to show how that's happening. Okay, so about 5.2% interest would produce a $200 increase in the investment over a 5-year period. Now, a different principal amount would have perhaps taken longer to grow to $900, some shorter, even if it was the same interest rate. So that's generally how financial problems work, particularly where we're solving for the interest rate, is roots are going to be involved, and we're going to have multiple steps to isolate our value for I. So again, this little flowchart or arrow diagram is useful to just plan your strategy for how you're going to get your value, so that you're clear in the end that you're going to be 3 steps away from getting the final value. So in the practice worksheet that I've given you here, this is very similar, except we're specifically told that the amount is going to double. Okay, so we want to double the value. That tells us that, okay, we're beginning with our principal amount as our current value of $500. And when we double it, the future value is going to be twice as much as the principal value, which would be 1,000. Okay, so I'm showing how to get the amount. The time, we're told here, is 7 years. Interest is being compounded annually, so there would be 7 compounding periods since it's annually. And we've got the formula again. I've introduced it to you before, so we're going to be putting in what we know. We have 1,000 being equal to 500 multiplied by 1 plus I to the 7. Okay, now as it turns out here, what we're really trying to solve for is what is the value of I that makes 2 when we raise it to an exponent of 7. So what I'm doing in between here is I'd be dividing both sides by 500, and that would produce 1 plus I to the 7. And again there, your arrow diagram, starting with I, the first thing you're doing is you're adding 1, you're multiplying by 500, or sorry, first thing you're doing is after adding 1 is you are taking that result and raising it to the exponent 7, then you're multiplying by 500, and that produces the future value. So to get the future value, you're going to be dividing by the principal. Then you're going to be taking the 7th root. Then you're going to be subtracting 1, and that produces I when you start from A. So in reverse, first step I've done, I've divided by the principal value. Check that off. I'm going to now take that and raise it to the exponent 1/7. That's going to cancel out the exponent of 7 and give me exponent of 1. And then finally, I'm going to subtract 1. And that will give me I. So 2 to the exponent 1/7 is about 1.104. Okay, so that means I is about equal to 0.104, and that would be 10.4%. Again, multiplying 100 to go from decimal to a percentage. Okay, notice there, 1/7 is not a terminating decimal, so don't use the decimal equivalent of that. Just use 1/7, use a fraction button, use your brackets, and make sure you're actually covering that whole fraction as you apply the exponent. Number 12. Let's look at this one next. So our last problem for this video lesson is just going through an application here where we're solving for another A, and this one would be the area inhabited by honeybees. So it was thought that in the early 1600s people brought honeybees over from Europe, and there was an initial colony, and then they spread out, and the growth of a living system usually follows exponential growth through reproduction. So we have this formula we're told would model the area that the honeybees inhabit after T years. So we're trying to model this honeybee population growth where we have 0.59 as our base and then T over 2. So when T is equal to 1 in part I, then we'd be trying to solve for basically just the 1/2 exponent on 9, which would be, again, we could probably avoid using a calculator entirely here because this is the square root of 9, using our exponent law that a to the 1/n is the nth root of a. So when n is 2, then it's going to be the second root or the square root. So half of square root of 9 would be half of 3. So it would cover approximately 1.5 hectares of land after 1 year. Okay, straightforward. Now in part 2, we're using t equals 3. So since the numerator is our t value, then that's going to produce 9 again as our base, an exponent of 3/2. Now 3/2 has to be handled using the exponent law a to the m over n equals, again, the nth root of a all to the m. Now in this case the base is 9, so I would rather take the root of 9 first than to apply the third exponent on 9. Okay, we saw that before in the previous video. So here we don't want to be dealing with 729. I would rather deal with the square root of 9 cubed. And again, square root of 9 is 3. And 3 cubed is 27. So again, we're pretty much able to solve this problem entirely without a calculator because we know our powers of small numbers. So the area of this one, I'll call A2 all the way through. And I'll call this A1. Here, their area is going to be half of 27, which would be 13.5. hectares of land. So only 2 years later, and the amount of coverage here, if we look at it as a factor, it's almost 10 times as much. 13.5 divided by 1.5 actually is exactly 9. So our area of land has increased by a factor of 9 after just 2 more years. Okay, so that just shows exponential growth, which we'll study a little bit more in chapter 5. Okay, so here we've been able to use both of our exponent laws for rational exponents. We've done an application problem. We've looked at financial application with compound interest. We've reviewed. Let's go back at this point now and tackle this question here. So here's our formula. We have 3 exponents. 2 of them are integer exponents, the 10 and the 7. Those are integers, and then the 1/6 is, of course, a rational. There's a symbol for that in math. It's Q. Rational numbers are Q values. So what would be one way of rewriting this formula? So we have the speed of this land animal is 0.783. There's nothing we can do with 0.783, and we want to make real clear here that this exponent of 1/6 does not apply to the 0.783. Okay, the base that it applies to is quite clearly indicated in brackets, so we have no choice there but to only apply the 1/6 exponent to our rational expression s to the 10 over h to the 7. So there's 2 things we could do here. Right off, we could take the 1/6 power and apply that as the 6th root. Okay, that would maybe be the most obvious change to make. If we were to do that, then we could leave it at that and say, okay, I'm going to have to calculate the value of that, and then I'm going to have to take the 6th root, and then I'm going to multiply by 0.783. We could also apply, okay, so that's sort of attempt number 1. From there, we could say, okay, attempt number 2, or version number 2, we could take our factor of 0.783, and the 6th root of a fraction is really comparable to the 6th root of the numerator divided by the 6th root of the denominator, because the exponent 1/6, because it applied to a fraction, we could really say it applied to the top and the bottom, and we can independently apply that to the numerator or the denominator. Okay, so this is really version 2, where we're separating this out now into 2 different 6th roots. That probably is not preferable over version 1. Okay, but what I'm doing here is I'm just using what we know about exponent laws to see if we can simplify this in different ways. Okay, we can compare them later to see which method is the easiest to evaluate. Okay, from that version 2, I could probably say, all right, again, my factor is not going to change. I could write this entirely as rational exponents and integer exponents and no roots at all. And I would have h to the 7 to the 1/6. And that probably is what directly would apply from the very first step up here. Is we could have said right from the get-go, we could have taken that 1/6 exponent and applied it directly to the top and the bottom, and that would have produced the version number 3 here. Okay. From there, I think it'd be natural to look at in the 4th version here, saying, well, okay, that means that my land speed could be 0.783 multiplied by s to the power of power would require me to multiply my exponents, and I would get 10/6 and 7/6. Probably at this point kind of running out of options unless I want to maybe take advantage of what we learned before with the different possible ways of writing the rational a to the m over n. We can either think of it as the root first or the exponent m first. Okay, so in this case it's root, then your exponent, whereas this is the exponent, then the root, or the radical. So if we try to make use of that, again here, we're just trying to apply what we know about the exponent laws to write things in different forms. Maybe one more, at least. We could say our fifth variation here might look like, okay, I'll take my 0.783, no change there, and I'm going to first apply the sixth root, then I'm going to apply the exponent of 10, and again here, first I'm going to apply the sixth root, then I'm going to apply the exponent of 7. So what we've actually done is we've completely reversed the order of those two operations from the very beginning, whereas we started with first the exponent, then the root was applied. Now we've got the root, then the exponent. So that's a fifth variation. Probably at this point, you know, the only other thing we can maybe do is just say that if there were one more version possible here, and this is a bit of a stretch, is that really we've just got one fraction. We've got 0.783 times s to the 1/6 to the 10th, and we have h to the 1/6 to the 7. Now eventually we're putting in the hip height and the stride length to solve for this land speed for this animal. So it doesn't really matter. Any of these variations requires putting in a value for s and a value for h. If you're unfamiliar with your calculator and you didn't know where the root buttons were and you didn't know how to evaluate a radical on your calculator, probably version 1 would be and 2 would be the least desirable to use because both of these rely on radical operations, okay, directly. If we wanted exclusively to use an exponent button, I would say versions 3, 4, and 5, and 6 really all use simply exponent button. And I would say, other than that, there's not a whole lot of difference between them. Probably version 4 would be the easiest one to do if we just wanted to put in one exponent. I think you can see clearly that you're taking your stride length and you're raising it directly to 10/6, which on your calculator you could make sure was a fraction, brackets around it, and then you'd be dividing by the hip height h raised to the 7/6. So this might be my preference right here as the easiest one to actually calculate. I think there's more buttons that you'd have to press if you want to enter in a root or a radical. Okay, so that's a little bit of review and a little bit of application. Again, going back here, this is where the chance for you to really strengthen your skills on this. This is a pretty difficult set of exponent laws, and students usually coming out of grade 9 and 10 are pretty comfortable with the basic exponent laws and exponent definitions, and this is definitely going to add a little bit more diversity to your skills so that when you work with exponents in college beyond this course, you'll be able to handle anything. Okay, so see you in class tomorrow.